Good morning. I'm Jim, an office year grad student Green Group. And as well as I mainly work on an experiment to quantify gravitational kinetics. But today I want to share a different project, which is a modeling project focusing on aromatic formation in fuel-rich methane, basically like fuel natural gas combustion, and by using RNG. And all the details are provided in the paper here. So if you're interested in more to understand it more, you can take a look at it or ask me any questions afterwards. So to start from like this project, why we care about like natural gas combustion in like fuel-rich condition, it's because like natural gas production has increased in the past decades by a significant amount, and it is expected to keep increasing for the following years. And that comes to the decreasing price on natural gas. So industry, a very common idea comes out would be how can we use natural gas to produce some valuable chemicals. And so one of the process is called partial oxidation, where more natural gas flows into the reactor than oxygen to create a fuel-rich condition. And for this kind of process, syngas is the main product, which is CO plus H2. And also acetylene and ethylene, like these C2 chemicals, are also very valuable. However, there will also be soot formed in the reactor, which is usually undesired product in industry. And in Green Group, we already have basically a model in ChemKing as well as introduce like the software. We can do chemical process modeling to model a pilot plant from in our sponsor side. And you can see you can have a mix of different gas flow and have some second cracking gas feeding, and the reaction can happen here. So this one can have a very good it's a very good model to predict the temperature profile and also have a decent amount of product prediction as what they measure in the pilot plant. However, for this kind of process, that time we were not able to predict aromatics formation. So that's another big topic we want to further dig into, because aromatics are very important, leading to soot formation. And that's what you can see here. Normally in combustion process, it starts from fuel and oxidizer, and in our case will be methane and oxygen. Once it starts reaction, other small molecules will form. And once it reaches the step to the first aromatic ring formation, which is benzene, and it can start to further react into larger species, which we call polycyclic aromatic hydrocarbons, PAH. And these PAH can further coagulate or condense into large particles. And these large particles, called soot, will cause serious air pollution, and it's not good for human health, and causing global warming as well. And more importantly, for industry, it causes clogging and lower the efficiency of the whole process. So to have this brief introduce of what we want to model, then we can set a target. Basically, we want to have a chemical mechanism that can measure major reactants, which is methane and oxygen, and of course the major products, CO, CO2, H2, and H2 as well. And other intermediates, including C2 chemicals, because these chemicals are valuable in either polymer industry or to generate other chemicals. So we want to know in what condition we can maximize the yield of these C2 chemicals. And aromatic radicals are important because, as we say, these will cause soot formation. So we also want to know in what condition we can minimize the formation of them. And to successfully predict all of them, we need a mechanism which has accurate kinetics, reliable thermal chemistry properties, and also we want some experimental data to validate our model. So luckily, about 2-3 years ago, there's an experimental group in Germany. They did experiment. It's like exactly the same condition we want to model is BH4 partial oxidation flow reactor. So basically, you can see the equivalence ratio is 2.5 for all the cases they study, which is a fuel-rich condition, and they provide very detailed like how many the flow rate of each of the components, and they also added some different additives like CO, CO2, or C2H2 to see like what kind of like the product distribution at the end of the reactor. So what they use is a method to measure all these species concentration, including major reactants and products, intermediate and large aromatic species. So, and they also provide experimental details, which is very useful for us to run the model in RNG. So, with this experimental data, we also have all of this concentration. Then, what we want to do is to run an RNG job and can generate a model that can capture all the chemistry inside. So, to start from, I think because we already have some basic idea on RNG. So I think here I just show like the input file we prepare for it. So in order to cover the whole condition operated in the experiment, first, because it's a flow reactor, in RNG now can only model batch reactors, right? So here we just transform the resident time of the flow reactor into the termination time batch reactor, which is about 2 seconds in the experiment. And we also have these 4 conditions. Basically, you see like this is the case 1 where they only have methane and oxygen with diluted by argon, and we specify the mole fraction. And the temperature is varying from like about 1100 K up to 1800 K, which is also the range they operated in the experiment. And because they also have different cases where they change the flow, add different additives. So we repeat these 4 reactors in RNG input file with different inflow composition. Here, just to let you know, in one RNG input file, you can have multiple reactor conditions, not just one. So here, we feed 20 reactors in total in one single RNG input file in order to capture everything. And here, you might also notice we have some zero concentration species. That is basically when you know some certain species might not have a significant concentration, but you really care its formation, then you can seed it with zero concentration. Then RNG at the end will definitely include this species in the model. So it's kind of the trick you can play around with when you actually work on certain projects.
How to get that temperature in experiments?
The temperature, so you mean how they measure that?
How they make that?
Oh, so they just, so this is, yeah, maybe I should introduce more. So this is a flow reactor. So they set, they give a set point of the temperature, which is varying from 1100 to 1800 K, and they measure temperature profile from the first, like the beginning of the reactor to the end, which is like more than, it's about 1.5 meters, and then measure the temperature every 1 centimeter. So that's for when we actually want to model this process, but in RNG, we just assume it's an isothermal batch reactor. So because we know the temperature range, so we just use different reactors to cover that range. You don't need to, I mean, here we just provide 4. You can also provide 10 if you want to have like a finite range within each of the reactors. Okay. Then the second part.
Question from webcast.
Yeah.
How can you feed multiple reactants in the input RMG file with different initial properties of temperature and pressure?
With what?
So how do you feed multiple reactants with multiple reactors?
Okay, so each of the reactor, this section is independent in RNG input file. So you just basically change the number here, like change temperature or pressure or like the initial mole fraction. So each of them is independent, so you don't need to worry about like you have different feed composition. You just give the reactor composition.
And this is all in one input file, right?
Yeah, in all one input file. Yeah. And the second part, so when we want to start, we are going to start the RMG simulation. We also know that small molecule chemistry is very hard to predict. Even though you have a very good quantum level of theory, so take this reaction like methyl recombination. It's like a very early reaction could happen because CH4 decomposes into CH3 and H at high temperature, and CH3 will immediately react, like, can self-reaction to form this. So this is definitely a very important pathway. And what we can see, people have done many either experimental measurement or like computational work, and you can see they still vary from like a factor 2 or 3. It might not be a very big difference for large molecules, but for these small molecule chemistry, they are so sensitive to all products formation. So even the factor 2 or even factor 1.5 could totally change the product formation or the chemistry inside. So here we found there's a published model called FFCM1 from Stanford. They basically focus on the chemistry from C0 to C10, to C2. And they did not only like a quantum calculation, but also experiment. So this model has been validated carefully, and it's a pretty well-known model in combustion. So with RMG, you can have the feature to provide thermal or reaction library. That means for thermal libraries, the properties from the library will be prioritized and grouped as a 50x estimation. So that means you trust numbers of the thermal property in there more than RMG estimation. And you can also provide reaction libraries where the rate coefficient, rate constant from the given library will also be prioritized in RMG's own estimation. So here you can see what we did is to provide FFCM1 as the top library, and also other libraries we found could be very useful. And here, the second part that we set the maximum carbon to be 7, because in RMG generated mechanism, we want to at least have benzene formation, and benzene has 6 carbon, right? So you here you definitely can set like larger number to have more species, but here we just focus on benzene formation first in RMG generated mechanism. And another question we want to ask is like, do we need to consider pressure dependence? And that probably was not mentioned in previous section. And to simplify it, usually when you know kinetics is expressed by Arrhenius equation, right? So it's only temperature dependent. You can see that like when you change temperature, different rate coefficient would come out. However, at some conditions, especially when temperature is really high, pressure is low, or your species is small, kinetics would not only be affected by temperature, but also pressure. And here, this is what people provided in literature. You can see above this line is the region where pressure dependence is not important. And down here would be the condition where pressure dependence needs to be considered in your mechanism. So here, a very typical condition, 1800 K, 1 atm, we can clearly see it's definitely under the line. So that tells us for our condition or the experiment we want to model, we should turn pressure dependence on. To do that in RMG, you only need to add one more section in RMG file, which is the keyword pressure dependence. So then you can provide, there are in total 3 different methods you can choose to consider pressure dependence. And modified strong collision is the most stable one, so I will recommend you start from this one. It may not be the most accurate, but at least it's the most stable, so it won't crash so easily. And yes, also different feeding options. One is called Chebyshev, the other is Arrhenius. Arrhenius is also called PLOS, if you have heard that before. So here I use Chebyshev because according to our experience, Chebyshev is better to fit kinetics within the range the range here I'm providing. However, even though you want to model a process maybe only 1 degree over like 3001 Kelvin, then shear differential will totally give a very crazy number. So it depends. So that's why here I try to provide the range to be large enough to cover all kinds of situations. Definitely 300K is high enough, and room temperature combustion definitely will not happen below room temperature, and pressure from very low 0.1 bar to 100 bar. In case they change for like our sponsor, they change different reactor conditions, we still can cover them. So so talk about preparing the RNG profile, and the next step will be can RNG find chemistry like important when they actually running a simulation process. So here is the example of forming benzene. Start from propargyl recombination. So propargyl is a C3H3 radical. It has 2 different forms. You don't need to know too much details in there. But this is the pathway people already summarized many years ago, back in 2003. However, you can see many of these elementary steps, there was no family, like reaction family in RNG defining this type of reaction. That means if you run RNG start from these 2 species, RNG has no way to find the product here. So that's a very important question that for us to solve, right? So what we need to do is to teach RNG new chemistry. And how to do that? For example, we have a reaction from here to here. You can see 2 radicals, like a carbene species, and directly form a double bond here and form benzene, right? So, of course, you need to change some code, but here I just show the simplified idea. For this kind of reaction, you just provide a different family in RNG. So you define the family, say, okay, for any kind of reaction with the carbene shifted and form a double bond, we call this reaction, this family singular carbene intradisproportionation. Okay, and after that, RNG know this type of reaction could work, but it doesn't know anything about the kinetics. It doesn't know how to estimate the rate. Then you need to train RNG with some calculated or even experimental data people measured at high pressure limit kinetics. And here is what we trained before. So basically, so you provide the reaction, and also you need to tell RNG like how does this species and this species look like by using some species dictionary. And also a rate is here, it's in Arrhenius form. So this is what you can put into RNG. So once you train RNG, and this session, and I think after my presentation, training reaction will be introduced in the next session, so you will learn that more. And for any train rate, it will be used for future RNG estimation. So let's say we train everything here on the family, on this like potentially surface, and the next version of RNG, when you find these 2 species, it can know the reaction like all the pathways here. So, and we can also have accurate kinetics. So that's how we do that to train RNG, and also we do that iteratively for any sensitive reaction we observe in the modeling process. So let's see quickly about the modeling results. So this is the mole fraction profile for CH4 and O2 as major products. Here, the x-axis is the set point of the reactor. So they vary the temperature from 1100K to 1800K, and the reactor has each of the specified temperature has a temperature profile. And at the end of the reactor, the major species concentration, and we compare that with our model at the end of the reactor. And we also have some other like dot lines, which are from other models that people already published, also focusing on aromatic formation in fuel-rich conditions. And the shaded area is the uncertainty of the experiment. Okay? So that can tell us, even though we are not exactly matching the experimental data, so at least we are fall within the experimental uncertainty. So you can see here, basically our lines, RMG solid lines, overlap with the experimental data, and so does the product formation here as well. The solid lines here, here, here. And also we can also do some quantification on ignition temperature, which fall within plus minus 15 Kelvin compared to experimental results. And also for C2 chemicals, like other chemicals is very important. We look at we model all the cases, but here we only show 3, which is case 1, 2, and 4. Case 1 is the most simplified case with only methane and oxygen. Case 2 is with CO2 added initially, beginning of the reactor. And case 4 is for C2H2 adding condition. And you can see the red lines now are our modeling results compared to experimental data. You can see the mole fraction is with like a very low concentration, like less than E-3, but we still can capture this formation pretty well, especially for acetylene. Other mechanism has like some overestimation. That means if you use the mechanism, you overpredict your formation of acetylene at higher temperature. That would cause some, basically you expect more product, however, in the experiment as that. And same thing for C4 chemicals, which are other intermediates, which they have even lower concentration, but here still can be predicted pretty well. And the first aromatic ring species was also generated in RNG, which is benzene. And you can see the concentration has been, the order of magnitude has been captured pretty well. Although there are some like overestimation at higher temperature, and that probably is due to some other pathway consuming benzene, which were not trained pretty well, and we're going to improve that further. So just to let you know roughly like the time scale, so to run this job, it cost me like about 5 days. Of course, I did running RNG jobs multiple times, but the final one took that long. And we have about almost 300 species and 3,400 reactions coming out. So it's still very, I would say, still very efficient, and you can capture so many reactions within like 6 days. So with that, we are satisfied with the aromatic ring formation up to like first aromatic ring formation. However, our goal is to further expand the model for even larger elements like naphthalene and benzene formation, which is C10 and C9 in the molecules. So for this one, of course, we can rely on RNG to further explore more chemistry, but that means we need to train not just important pathway forming these species, but also not important pathway, like negligible pathway, because sometimes RNG could estimate the very slow kinetics to be faster. Then you also want to train those reactions to be the accurate kinetics or accurate thermal, for example. So that would definitely need more and more work. However, we can expand the model by using a different method. So in literature, we already know for these 2 species we are really interested in, there are 10 dominant pathways, each with a very careful quantum chemical calculation published already. And these 10 dominant pathways, as long as we include it in our mechanism should be able to predict their formation accurately. So this is one of the examples called compound pathway. So phenol, like benzene radical, adding acetylene to form like species and further form ring close to be naphthalene. And this one is has been published already, and we can use the tool in RNG called RCAN. Previously it was called CANSON. I think people are now changing the name. And you can either input species energy, molecular information of collision model, which usually are given by the potential energy surface calculation. For example, you know the relative energy, 0, and the transient state energy, 3.6 here, for all of the species out there. Molecular information, I mean here, like vibrational frequency and moment of inertia, is kind of information for species. And then Arcan can calculate or estimate pressure-dependent rate coefficient. Or another strategy could, this is I think what IMG can do other than other similar software packages. So which is that you can use thermochemistry data estimated from IMG with high pressure limit kinetics. Usually high pressure limit kinetics are more available in literature because people usually don't report pressure dependent kinetics. Then you have these two, and RMG can also do estimation for pressure dependent kinetics. And that's very helpful, especially like not all literature will report very detailed molecular information unless you ask the author for furthermore. And so after that, we expand the model, and the model now has about 40 species and almost 7,000 reactions. And we can see experimental data scattered a little bit here because the concentration is a little bit closer to their detection limit. But we still can see the red line, which is here, these three are in-zinc formation. That's a pretty close prediction compared to the data. And also naphthalene, and the largest species we have is C12H2, which is ethylene. So at this point, we can say for the CH4 methane combustion, we have a mechanism which is pressure dependent, and we can predict up to C12, which is a fairly large pH species. So more than the accurate prediction, we also can learn a lot from RNG generated mechanism when you do pathway analysis. For example, when we have a benzene formation, then we at the maximum benzene formation temperature, we run the pathway analysis, and we not surprisingly found proportional combination to the leading pathway for this benzene. This is what we teach RNG before, right? And also the side reaction type. And each of them has a reliable kinetic we know from definition calculation or from RNG estimation. However, if you look at different mechanisms which we use to compare, they also have these pathways. They probably can also predict benzene pretty well, but for these reactions, when they provide only one single reaction, in fact, has only one temperature and activation energy barrier height. So that means first, it's not pressure dependent. So if you have a very significant pressure change, it cannot be captured. And second, these kind of rates are normally fitted from their experiment. So it could perform very well in certain conditions, but it's not adaptable to like other significant change. So, but of course, this kind of mechanism, like we call it like global fitted pathway, also has some benefit, which is that fewer species and number of reactions. Compared to the same pathway you see, we have like we only have one. So in terms of like running the model, this one could be definitely faster. But as you know, RNG is built based on elementary steps. So what we want to do is that we generate a very complete mechanism, and for the user, for using the mechanism, they can simplify it at their condition they want to study. So, but for the simplified mechanism, it's very hard for user to expand the model for different situations. So this is, I think, what RNG can still be very important in any like type of modeling. So at the end, I want to say thank you to my advisor, like Professor Green, and other collaborators on this project, and my sponsor, Savic. And here, if you have any questions, feel free to email me afterwards, or you can ask them now. Thank you.